Hello everyone. We're going to discuss section 8.3, multiple bonds, and this is specifically within the context of hybrid atomic orbitals. The learning objective here, describe multiple covalent bonding in terms of atomic orbital overlap. And then the second one there is something we might touch on a little bit, but not something that we need to focus on too much. So I'm not going to really include that as a learning objective. So what we learned in the previous section was that the hybrid orbital model does a very good job of predicting the correct geometries when we have single covalent bonds. We now want to see, can we stretch that to when we have multiple bonds, when we have double or triple bonds. So let's go ahead and look at an example, and this is one that we have discussed previously in an earlier video. So this is ethene, and we know that we have a double bond here between the two carbons, as well as within that double bond we have a sigma and a pi bond. So we know that when we have multiple bonds, that is how that will work. So can we explain having both a sigma and a pi bond using the hybrid atomic orbital concept that we've been developing in the previous couple of videos? So let's look at the hybridization and how that works. So we've looked at, so we know that we would describe this as being an sp2 hybrid based on having 1, 2, 3 places with electrons around that carbon, around each of the carbons actually. We would call it sp2 hybridization. So we're showing sp2 hybridization here. So we have the s orbital and 2p orbitals combined. And when we combine those, we get 3 sp2 hybrid orbitals as well as a p orbital that is unhybridized. So the way that this actually works is that in order for us to describe this multiple bond, we also use the unhybridized orbital as part of the model. So we can see that here. So describing the bonding between all of the atoms here, we can see all of these sigma bonds. So we have a bond between the carbons is a sigma bond, between sp2 hybrid orbitals, the bonds between the carbon and any of the hydrogens are sp2 to s orbitals. So we have a hybrid orbital and an atomic orbital overlapping to form sigma bonds. So we can describe all of the sigma bonding. And then we also have these p orbitals that are unhybridized on each of the carbons. So what we know is going to happen based on what we've discussed earlier is that these will overlap, these unhybridized orbitals will overlap to form a pi bond. And I want to take a minute to highlight something here. What we're showing here is a single pi bond. So the pi bond has a lobe above and a lobe below the internuclear axis. So there are 2 lobes to each pi bond. And so this is one bond. The blue and the red are both part of the same bond. And then the other bond is the sigma bond right in here, okay, which is the orange. So that's a sigma bond and a pi bond. Okay, so that did a really good job for a double bond. Let's look at a triple bond. So here we're looking at, this is acetylene. Again, you don't have to know the name for this, but this is the Lewis structure for it. So can we describe a triple bond as well? So the hybridization on the carbon, so we know it's linear because we have 1, 2 places with electrons. So we have sp hybridization. So 2 places with electrons is sp hybridized, so that takes two orbitals, the s and the p, and puts them together. And then we'll also have unhybridized p orbitals. So one unhybridized p orbital is this red on the top and this blue on the bottom. The second unhybridized p orbital is this red in the front and this blue in the back. I think it would have been a little bit clearer if your book had maybe the arrows going both here and here, as well as here and back here, in terms of what those p orbitals are. One of the big misconceptions that comes up when we talk about hybrid orbitals are, how many things are involved in each orbital, because the hybridized orbitals and the p orbitals look somewhat the same, but they're actually very different. So the SPs are showing only one lobe apiece, whereas for a p orbital, you always have two lobes. So what we can describe happening here is we have each of the carbons, they have an overlap between the atomic orbital on the hydrogen and their sp hybrid orbital to form a sigma bond, very similar to what we saw in the previous example, but in this case we have it's sp instead of sp2, but the same thing can happen. And then as well we have an overlap between the sp on one carbon and the sp on the other carbon to form a sigma bond. So this is an orbital overlapping here, so this is a sigma bond. This is a different orbital overlapping a different orbital to form a sigma bond. So we have two SPs on this carbon, and then we have two on this one to form those sigma bonds. So we have three sigma bonds that occur here. And then we have the pi bonds. So what's happening is we have these unhybridized p orbitals. So a red and a blue represent one unhybridized, a red and a blue represent the other unhybridized, and they overlap with each other. So what we're showing here is we're showing two pi bonds. Each pi bond is two lobes on either side of the internuclear axis. So this is the internuclear axis, is basically where we see the orange. We have the sigma bond right along that axis, and then we have a sigma bond to a hydrogen, sigma bond to a hydrogen. Above that, we have a pi bond. So this red and this blue represent a pi bond. And then 90 degrees from that, we have another pi bond. The red in the front and the blue in the back represent a second pi bond. So remember, with pi bonds, you have two lobes with a node along the internuclear axis. With a sigma bond, you have it's along that axis where the node would be for the pi bond. So it looks like we can very easily describe double bonding and triple bonding using this model. So it does a very good job of describing that for us, and in fact I think we have a better understanding of what pi bonds are with this model than we maybe did with the valence bond theory. Okay, so it does pretty good at that. We do, however, run into a little bit of difficulty when we start seeing resonance show up. Okay, so this is something we'll discuss a little bit in a forthcoming video.